All right, before the break, we were talking some more about the productivity software, some of those things. Looked at a couple points on presentation software and spreadsheets. But our main topic this week is going to be data. And I mentioned it earlier, the statewide course shell, the one for IB Online, so that all of the online courses are covering the same thing. That's a large thing, it gets approved by committee and make sure it's all okay and stuff. But the current, we used to spend like a week, sometimes 2 weeks talking about binary code in the SDEV 120 class. But as things moved from 16 weeks into 8 weeks, stuff got shuffled around, and that class has a lot to cover. The way I describe that class is it's computer logic. Basically, it covers how we feed instructions into a machine. We do it in the format of programming, but really what we're looking at is how do we feed instructions into a machine? How do we tell the machine to do what we want it to do? And obviously programming is the main one for that. And when we get practice with that main concept, and binary kind of got pushed to the side, there might still be a quiz on it that's like a short quiz, one of the 5 or 10 question quizzes, but most of the content for it got moved over to the discussion board and kind of like go research it yourself. And so while talking to other instructors, we're all kind of in agreement that binary is kind of important. So we want to work it into other places and see it when we can. So I wanted to talk about binary representations. It's not something you're going to be tested over in this class. So if you have not seen that class yet, think of this as preview mode, because obviously we're talking on day 1 about flipping switches on and off. So we're dealing with binary states, and we need to build up from those binary states. How do we make on-off switches represent the data we want them to do? And we do so using numbers. What I have in my notes here. So we discussed how computers use patterns of switches to symbolically represent raw, out of context facts that we know as data. Just like I'm using lines on a board here. Binary encoding. So just like when I make the lines on the board here, and in a certain pattern, you all know what that pattern represents, at least how to say the words. We want to do the same thing with a bunch of on-off switches. We drew one the first day, right? That big messy one. So we have like some battery in the circuit, and we'll come over, and maybe our first switch here is off. And then we have another switch that is on. Another switch that's off. I think this is the one I did the first day, and then we'll draw another switch turned on. So same way I'm using lines to represent our spoken language here, we want this pattern of switches to represent our data. In particular, this one means 5. And we want to know, how do we get 5 from that in a useful way, in a way that is meaningful enough with the rest of numbers as we know them. And then once we have numbers, there's some other encoding schemes we can use. So that picture was complicated. That's why I didn't do the normal ask if it's okay if I erase this, because that's a complicated mess. We don't want to dig through circuit diagrams to figure out what's going on. So we need a better way to represent that. And we want to represent things numerically. So we want to use some of our digits. And even when we're not doing numerical representation, we still use our digits, because our starting 2 digits are going to be 0 and 1, which also happen to be 2 of our easiest symbols to draw. So even if we're not talking about numbers, we still use those symbols because they're really easy to use. So let's take a minute to go over these patterns of binary code. If you haven't seen it yet, it's actually something you already know. You're probably just not aware that you know it. So let's start with the numbers we know. 276. I'm going to write a little N down here. This is a standard way to represent that we're working in base 10. That's the numbers we know. If I write this, you all know what it means. But it's probably been quite some time before you focused on, or since you focused on the details of what that means. What it means is we have 200 plus 70 plus 6. And from those numbers I just read off, what they have in common is those are all multiples of 10 or powers of 10, right? So it's something in the hundreds, just like 10 squared. 70 is 7 tens, or 10 to the first power, and 6 ones, which we can also represent 1 as a power of 10 in a math rule, but you probably haven't seen in a while of it, unless you just happen to have had a math class very, very recently. So what this means, I'll write it out, is we have 200 plus 70 plus 6. And they're all powers of 10. So this 200, we could really write as 2 times 100 plus 2. 70 is 7 times 10, and 6 is going to be 6 times 1. And we're humans, right? We have 10 fingers, which means 10 is a nice, easy number for us to work with when we work with numbers. We can count things on our fingers. There's other ways we can count on our fingers. You've probably heard of base 60. The Babylonian ones, they based everything off 60. That was counting on our fingers. I started pointing that out in class because people are surprised that 60 is counting on our fingers as well. But each one of our fingers has 3 sections, right? So if you count those, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, you can count to 12. And on the other hand, maybe use your fingers and count to 5. So we can count to 12 5 times, or like on a clock, we can count to 5 12 times. And I started pointing that out in class because a lot of people apparently didn't know that was based off counting on our fingers as well. But here in America, we do the easier one, right? We just use our fingers directly. So we got 10 of them. We want to base all of our numbers on that. So this meaning that we have here, we want to think of that as powers of 10. So 100 is really 10 squared. So when we write the number, what we have is 3 different columns, and each one's a power of 10. Like 10 squared, or 10 would just be 10 to the first power. And if you haven't seen it in a while, there's a rule in math that any number raised to the 0 exponent is a 1. If our exponent is a 0, it doesn't matter what number we're raising there, that's a way to write 1. I always like to think of it as we have something, otherwise we would have written a 0 here. With the little exponent, we can't really say what it is we have, so we just go with our basic number of 1. Then we have columns, each have different meaning based off the number, off a power of 10. We'll have 2 of those, 7 of those, and 6 of those. And then that just continues as we get bigger and bigger, right? And we have a 10 cubed, or 1,000, 10 to the 4th power, 10,000, and it can just go on forever, and we can write all of a digit in each column and represent each of our numbers. That sound familiar to everybody? Going back to elementary school, you probably just haven't paused and thought about what that meant explicitly in quite some time. I guess the last point is we're basing things off 10, so that's how many symbols we need, right? We need 10 symbols. which we're talking about numbers. So we need 10 numbers. And then we have that, we hit that slight discrepancy between our cardinal numbers and our ordinal numbers, right? Like 2 is actually our third number, because 0 is a number. So 0 is our first number, then 1's our second number, 2 is our third number. So we want to include zeros, so our 10 symbols are going to be 0s and 9. So otherwise we did a problem when we started down at that lower end. So we have 10 symbols, we organize them into columns. Based on each column is the power of 10, and those add up to do the math that we're familiar with from our daily lives. But there's nothing special about 10. We can use any number we want. What did I use in my notes here? 7. Lucky number 7. So we could do the same thing with base 7. Oh, another thing, base 10 is called decimal. The word decimal refers to working at base 10, where we put the little dot and then the fractional part. That's actually called the mantissa. And if we're going to work in different bases, it's kind of important to make that distinction. We can work in base 7 just the same. We list things out into columns. I'll put like 4 digits here maybe. And each column is another power of 7. And we always want our first column to be 1s. So that's going to be our base raised to the 0 power. And then we just walk up our powers. So 0 to the first power, 7 to the first power, 7 to the second power, 7 cubed, or we might want to think about the whole number, so I'm going to write them in base 10. So we have a 1s column, we have a 7s column, 7 squared is 49, or a 49s column, and 7 cubed is 343. Which sometimes what seems like extra steps is actually quicker, right? And that's what I did there. To find 7 cubed, I just took 50 times 3, or 50 times 7, 350. But that 50 is 1 too many, so then subtracted off the 7 extra ones. So sometimes the extra steps actually make things shorter and easier than trying to calculate that all manually directly. So I'm just going to write a random one in here. So base 7, which means we need 7 symbols. They need to represent numbers. So again, we'll use 0 as our first one, and 0 through 6 would give us 7 symbols. So if I write a couple of those symbols in here, maybe a 0, 3, 4, 1 is what I put in my notes here. And then normally we would, if we're working in multiple bases, we do a small subscript to say what base that is. So we want to, but we're Americans, we work in base 10. So we want to know what this number is, 341 in base 7 in our normal base 10 numbers. And to do that, we can follow the same pattern we did here. Just take what each column means. Only it has a different meaning than the one we're used to. So we don't have any 7 cubes. I just wanted to make sure that the pattern goes on forever, just like with the numbers we're familiar with. We just keep adding another power to whatever our base is. So it looks like we have 3 in the 49s column, plus we have 4 in our 7s column, and then we have 1 in our 1s column, plus 1 times 1. And what do we get out of here? 3 times 50 would be 150. 49, so we were actually 1 too big there. So 3 times 50 and then minus the 3 extra ones from the rounding to make it easier, would give us 147 plus 4 times 7 is 28 plus 1 times 1 is just 1. And now we're all in counting base 10. That's right, little 10 there. Because now we can add those up. We can probably see it in this one, but since we're talking about number systems, let's go through the whole thing. You probably remember back in elementary school, we can line up our columns because we have that same meaning in each one of these separate numbers. So if we line up our columns, then this 2 in the tens column lines up with the 4 in the tens column here, or the 7, 8, and 1 all in the ones column, all line up there, and then we can, that does not look like a 2. Then we can just add up down each column. So 7 plus 8 is 15, plus 1 more is 16, which is too big of a number to fit in one column, right? So all this stuff back in elementary school, kind of ringing a bell somewhere there. So we can carry that. So it's too big for one column, because 16 means we have 10 plus 6 more. So we can put our 6 in our ones column, but our 10 has to come over to the tens column. So the only one's going to carry 1 plus 4, 5, 7, and then just the 1. So 3, 4, 1 and base 7 is the same as 176 and base 10 that we're measuring. Does that ring a bell for everybody? Remember doing that stuff back in elementary school, going over the details of it? But you probably haven't seen the haven't thought about the finer details in a while. And all our rules still hold. So what I did here, we can do that in base 7. Well, we know what 176 in base 10 is. So what if we did, say, 176 minus 83, those are both base 10 numbers. Numbers we're familiar with. What if we needed to do that subtraction, but we're working, everything we have is in base 7? Well, it's still work out the same. We know what 176 is. That's going to be 341 in base 7. And if we subtract 83, but we need to know what 83 is. And to do that, we just fill out our columns. So we have our 7s column, and our 7 squared column, or whoops. We have a 1 column, then we have a 7 column, then our 7 squared column, or 49. And we have these symbols to work with, so we just have to figure out how many of each one we have, how many we have in each column to add up to 83. The easiest way is to start with our biggest numbers. We want 83. So our first column, we have 49. There's definitely 83 is bigger than 49, so we can fit one of those. But 49 times 2 is 98. So that would be too big. So we can only have 1 there, which is just a little scratch work off to the side. So we're looking for 83. And it's like we found 49 of them. What's that leave us? 4. Oh, then we didn't do subtracting yet. 3 minus 9 is kind of too big. So way back in elementary school, what we do is borrow from the next column, right? 3 minus 9, 9's too big to subtract from 3, but we can borrow 10 from the next column and leave us, then we have 13 minus 9, which can easily be subtracted, and just leave us 7 in the next column. So we still have 34 to account for. So how many can we put in our second column here? Does anybody see where this pattern is going? Or know know it from before.
I do
A
not.
little bit, not much.
Just the idea kind of makes sense. We're going to look at it a couple times. That's why we look at it in intermediate. We're doing the same thing we're familiar with our numbers from base 10, only with a different base. Because any number works. All of our patterns still work. So we want to know how to represent 83 in base 10. Or sorry, 83 in base 10, the number we know, but we need it represented in base 7 so we can subtract it from this. And well, we know there's going to be a 1 in our first column. Gives us 34 left to find. So 7 times 5 would be 35, right? Using the numbers we know. So that would be too big to fit in that column. Or if we put 5 there, that's more than the number we need. So we can fit 4 in the 7th column. Usually I like to show it at least 3 times. The one we know, the intermediate one, and then the one we're actually looking at here, the one we're actually heading into. So after 3 times, you'll kind of see how the patterns apply everywhere. So we're just trying to represent this number differently. So what we mean when we say 83, but we need it represented with a different set of symbols, a smaller set of symbols. And we find it still kind of do the same thing. Find that meaning, we put as many as we can in our biggest column, and then repeat that until we get kind of something in every column to represent that value we're considering. So 7 times 4 would be 28, and 34 minus 28 would leave us 6 more for our 1's column. So that is just some symbols that carry the same meaning as when we say 83, but written with a different base system, written in a different numerical system. Then we can line those up in columns the same way we did back in elementary school to add and subtract things, so that we can carry out this math. 176 minus 83. The words for the numbers we know represented in base 7 would look like this, and then just do our subtraction like we did way back in elementary school. 1 minus 6 is going to be, well, 6 is too big, so we would have to borrow from our next column. We're going to take one of those away, and our base, no matter what number system we're working in, our base will always be written 1, 0. So whenever we borrow, we're borrowing 1 from the next column, but with base 7, that next column isn't 10 that we're borrowing 7. So here we have 7 plus 1, or 1, 0 plus 1, actually gives us 8. Right? So we have that change in the meaning of the symbols we're using. So when we borrow, then now we can subtract, because 8 minus 6 would be 2, and 3 minus 7, again, it's too big. So we'll borrow 1, but it's not 13 like we know about it because we're working with a different system. We didn't borrow 10 from the next column, we had to borrow 7 from our next column. So really this is 7 plus 3. Which then we can subtract the 3 there, and then 2 minus 1 is still 1. So those same rules still apply. Like if we check the meaning of that number real quick, 1 in our 49s column plus 3 in our sevens column. Plus we have 2 in our ones column. I can't remember, and so I'm going to skip the times 1. So what is that? 49 plus 21 plus 2 is 72. That doesn't seem right. Oh, whoops. I'm sorry, I wrote this number down wrong. That was supposed to be a 4. So when we subtract, we get a 6 there. So 49 plus 42 plus 2 should give us 93. Which is why I had that in the notes, because that's kind of confusing, right? But if we check back to our original one, 176 minus 83 would be 93. We're not going to work in base 7. That was just an intermediate one to see that all of our rules still apply. Back over to the base 10 side, do you all remember all those rules back from elementary school and how we would do everything by hand and what those mean? That's the important part. This is to view them a couple times, but well, I was copying from having them already written down on a piece of paper and still made a mistake in there. It gets confusing when we look at different systems, but all of the rules that we know from math still apply no matter what we base our number on. Numbers and math are 2 separate things, basically. Since we learn them together when we're growing up, when we're little kids, we learn them together. But the rules of math are separate from our numbers. It's an important thing in understanding right there. Is it okay if I erase this and get to the system we actually want to look at now?
Yes.
I just noticed there's a couple of yeses in the chat room. So yes, kind of confusing when we do different systems. I like to do the intermediate one just to see the rules multiple times so that they're fresh in our mind, because we probably haven't actually explicitly sat down and done them since what, like 3rd grade, maybe 4th grade. Oh, there was a rule that I forgot to put there, which you may have never even heard as a rule, because it, if we're working in base 10, right, 22 plus 33 plus 44, we can keep adding numbers together, right? Plus 17 plus 8, and we can just keep stacking them up, and it still just goes down our columns like we know, right? So we want to be careful with this. You probably never heard the rule, but you should never do that more than 10 times. You may have heard that, which as a rule across different bases, you should never do that more than your base. So on the next one we write up here, I think y'all already know, for machines, we want to work in base 2, and that don't add together more numbers than your base is really going to show up when we only have 2 of them. So if you have 3 numbers that you want to add together, and you're going to do it by hand this way, going down the columns, you really want to add the first 2 together and then put the result of that with the 3rd number. If you do more than your base, you risk carrying multiple columns over. Okay. If we add these up, you might have to carry something over to the next column, add up, carry something to the next column, add up, and add up. But you don't want to end up carrying something 3 or 4 columns over and then work on this column and have things mix and match as far as where they carry. So to avoid that, there's a rule that you should never add up more than your base, which definitely shows up when our base is 2, because humans can handle a lot more than 2 numbers at a time. So, but any number we choose works with all the rules of math that we know. How long was that? And we can work in the columns, and then in our machines using switches, we have binary states. Right? That switch is either turned on or turned off. So we can use that on or off state, which is a little technicality. If you actually get into electrical engineering, it's not on and off, it's source and sink. But for our classroom here, we're going to say on and off every time. We're going to call it on and off, but there is a technicality there from advanced electrical engineering. As long as you remember, there's a technicality in the difference. For example, on your screen, the monitor you're watching this video, this Zoom call on, exactly half of those LEDs turned on when they were sent to 1, and exactly half of them turned on when they were sent to 0. So technically they mean something different, but it's confusing enough as it is. So with just keeping that technicality in the back of your mind, we're going to say 1 is on and 0 is off, and just represent things. And then we can use those patterns of switches, like that messy one I drew up there a few minutes ago, to represent any number we want. Let's say we have 176 in base 10. We want to know how to write that in binary. Well, we do the same thing. We set up columns for each number to go in. Which we only have 2 symbols, so we need a whole lot more columns. And this is actually a lot easier. That's another reason I like to go through the intermediate one, where it's a mess and mistakes almost always happen. It looks confusing, but we talk about the rules. This is actually a lot easier in binary. We set up our columns. Again, we have a 2 to the 0 column, which we just have a rule that anything raised to a 0 power is always going to be a 1. Then we have a 2 to the first column, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th column, and we can keep going as we need more. But 8's an awful lot to write on a board. Actually, I think after this number, the rest of my notes, I'm only using 4 bits for anything written on the board. Because we can see the concepts if we only go up to the first 4 bits. That's enough to see concepts, and it just repeats over. But we need to figure out how many we have in each column in order to add up to 176, just like we always do in base 10, or like we just saw in base 7. But it's actually easier because we only have 2 possible values. We're looking for base 2, so binary, so we need 2 symbols, which we'll use 0 and 1. And then the nice thing that makes it easier is another binary state that we often deal with is yes and no. So then instead of going through each column trying to figure out how many we have, right, like in base 7, trying to figure out how many we have in that 49s column, how many we have in the 7s column, it's a yes or no question. So we're trying to add up to 176. If we started our biggest, I'll write the numbers on here. 2 squared, we have a 4s column, and we have an 8s column. And in our society, you probably recognize a lot of these numbers. Then we have a 16s column. We have a 32 column, 64 column. We just double the value each time in a 128 column. So we'll just kind of go through here and see if it fits. So we're trying to add up to 176. Our first column is 128. Will 128 fit inside of 176? Anyone say yes or no? Yep. So it will fit, right? So with binary, we end up with yes or no questions. Oh, yes, we do have something in that column. So we'll subtract off the ones we've accounted for. Again, I'll do it all like we did in elementary school, borrow 10 from the next column, so 16 minus 8. Have 6 left over, 6 minus 2 is 4, 48. So we still need to account for 48 of them. So somebody else answered this time. Do we have anything in the 64 column? Will 64 fit inside of 48? Nope. So 0. So binary states, ones and zeros, we can assign different meaning to them. And as we're doing stuff, it's usually useful to do so, right? True, false, yes, no, up, down. There's lots of words we can put there that will help us make sense of the situation. We don't have any 64s, what about 32s? I saw a couple yeses pop up in the chat room. I think there's a long string of yeses in those in the chat room. But yes, 32 is smaller than 48. Subtract that off, and we're left with 16. Oh, there's our next column. So we still need to account for 16. Our next column covers 16. And 16. And we don't have anything left to account for in this particular number. So the rest of these are all going to be zeros. Does that make sense? You see some yeses or nos, or a little thumbs up icon, some of the emojis. Because that's an important one. That's how we represent numbers. Oh, nice. I don't see any no's in there, so I guess that's a good sign. It gives us a way to represent our numbers with those on or off switches. Kind of a mess. There's a couple other things we want to do there. Are we looking on that? Okay, yeah. Real quick here. Fractional values. I'm going to kind of jump ahead. Oh, did you mean to share your screen there, Michael? I think that was Michael. Somebody started sharing their screen. Do I have a stop button for that? Nope, I don't. Okay. There used to be a stop button. They used to have a stop button for that. So adding and subtracting still works. Real quick though, our fractional values are kind of the same. 3.14159. What we usually call decimal values, we want to be careful with because that's actually sloppy language. Decimal means base 10. So we can have those values smaller than 1, the things between 0 and 1, in base 2 as well, or base 7 or base 16, any of our number systems. And you might remember that when we did this in base 10, our powers of 10 just go the other way. So we have a 1/10ths column, then a 1/100ths column, or 10 squared, or a 1/10 cubed or 1,000ths column. And our power of 10 just goes to the bottom of a fraction, which we can also write with a negative exponent. If you haven't seen that, if you see a negative exponent, that means your number is actually on the other side of the fraction line. So like flip the fraction, get the reciprocal of it, or 10 to the -2, 10 to the -3. And those sort of values would be the same thing, only with powers of 2. We'd have a 1/2 column. in a 1/4 column, in a 1/8 column, and I'm looking at these numbers right here. I have them memorized, but they're written right here, so I'm just writing them the other way as the bottom of a fraction to represent the smaller values, and then we add them up the same way. We're not going to be tested over it, just so you're aware that it does still follow all the same rules. We're just using 2s instead of 10s, which gives us that nice yes/no question for everything we want to think about. Except that that's really long. It's going to add up, and it's kind of long, kind of quickly. So better ways to represent that would be nice. We'll see one here in a second. Another thing, just a quick note, this is not a new system. This was not invented with computers in the 1940s. I'm actually a math person, and math is very related to computers. So when I got my degrees, my first couple of degrees to teach math, the job of teaching software development opened up here. I started doing that, and yeah, I've since moved into an office and got fancier things written on my name tag. But back when I was getting my math degree in the history of math class, one of the things I had to do was this is how Egyptians did their math. Like us, they worked with base 10 because it's nice and convenient for our fingers, but Egyptian scribes would convert everything to base 10, base 2, do the math in base 2 with that yes/no situation, and then convert it back to base 10. So it is not a new thing. It was not invented with computers. Actually, electricity was the only new part in computers. Everything else was known about long before that. I'm gonna erase this. This was just some scratch work from finding that. Looked like that was making sense to everybody. And then we can do, I wrote encoding up here, right? I didn't write binary numbers, because numbers aren't our only type of data. But once we have a way to write our numbers, we can encode our other numbers really, really easily. Our other data really easily. For example, we can say, okay, the letter capital A, let's represent that with the number 65. In base 10, which in base 2, if we go through here, we wouldn't have any 128s. Oh, we would have something in a 64 column, but then there's only one left. So in base 2, we'd have 0, 1, 0, 0, 0, 0, 0, 1. And we can use that number in base 2 and just say that's a capital A. Capital B, well, let's, if A was 65, it would make a lot of sense to say B is 66, right? Which in binary is one more than this, so 0 would look like that in binary. Same thing, C, we could say that's a 67, and hopefully y'all can see where that pattern's going, right? We can just go through all the way through our alphabet, the symbols that we use to represent our language normally, and give each one a numerical assignment, and then add one more extra bit in for that yes/no question on yes, it's a number. No, it's not a number, then it must be a letter. And we can represent all of our data that way. Get all of our written language up here. There's a bunch more, ... A lowercase a. I'm going to drop the quote marks from that. That's really important in programming classes, but for here, I'm going to drop the quote marks. A lowercase a, we can say that's a 97. Lowercase b, 98. A lowercase c is 99, and just kind of go through all our alphabet that way. A space is 32. An exclamation mark is 33. Then we're walking across the top row of the keyboard with the shift key first. And like capital letters, then lowercase letters. Same thing with our special symbols. The shift, and then that key goes first. So exclamation is 33, @ symbol is 34. The one with lots of names, #, hash key, number symbol, whatever you want to call that one. The thing above the number 3 on the keyboard is going to just follow right in order. We go across there and then back to our digits as characters, so we can put them with our written language instead of our digits as the numbers that we do math with. And all of our symbols we use in English, there are less than 256 of them. So we can fit all of that into 8 bits, which was given the name of 1 byte. It's not quite enough for all of human language. That worked for America. So these numbers I was writing up here, that is Ascii Code, American Standard Code for Information Interchange. Which, when America and a couple countries in Europe were working on the early days of computing, Norway had to adjust their alphabet a little bit, but everybody else that was working there in those early days, the American symbols were fine. It's not enough for all of human language, so we extended that into Unicode. So ASCII is 8 bits, or 255 symbols, but humans have a lot more than that, so we extended to Unicode, which is a 16-bit system for encoding those. But it is an extension, it wasn't a replacement. So the first 256 symbols in Unicode are ASCII code, which that's the ones we need as Americans. But it's just a 1-to-1 ratio once we have our numbers. That's the main idea of it. There's a few other things that you'll see later. An important one will be 2's complement. That's an old math trick, so that we can do, so that when we add 2 numbers, we get the same thing as if we would have subtracted them, plus an extra digit. And then we can do everything with one single operation. We don't even need negative numbers. When you hear to think about add the negative, we can we complement one of them, and that's which is really hard in basic. It's complicated. We need a different definition than I'm getting ready to say here. But in binary, complement is really easy. Not complement with an I. We're not saying nice things about our numbers. Complement with multiple E's, so like complementary colors, or with numbers. In binary, it's just our other. If we have a 0, our complement would be a 1. If we have a 1, our complement would be a 0. So we do that, and that gives us what's called the 1's complement, or the first rank of complement. And then we add 1 to get the 2's complement, or second rank of complement. And then that would continue, but 2's complement's the one we really need, because that gives us a way that we don't even need negative numbers. We can, if we want to subtract, we take a number and it's 2's complement, and then we end up with what we would have got had we subtracted and an extra digit, which in computers is really, really useful, because then we can build all of our math from one single circuit, which is what an arithmetic logic unit does. But we're just kind of previewing the binary stuff, so get into preview of it. I guess, okay, so about 8 more minutes is what I was thinking. Is it okay if I erase this half over here?
Yes.
Yes.
Right, really quick, the rules that we know still apply for binary. We'll see those again. So if we wanted to say take 13, I'll make that smaller. I'll do it in 4 bits. So I wanted to take 7 plus 3. We know what it would be, and we won't have a huge string of bits here. If we wanted to add those, we just write each one in binary. So 7, we have 4 columns. We have a 1 column, a 2 column, 4 column, and an 8 column. Somebody want to tell me real quick what 7 is in binary? We have these 4 columns, and we're just asking yes or no. Do we have any 8s in this? Oh.
No.
The chat room stopped scrolling. No, we do not have any 8s. So we have a 0. Do we have any 4s in a 7?
No.
Oh, we would still have a 4, right? Okay, yes. Okay, that's where I was looking for. I was looking for the binary to pop up. So 0, 1, 1, 1 is 7, which is a nice pattern. 8 is a power of 2. So 1 less than that, if we added 1 to this number, we'd be at the next power of 2. So if you're 1 less than a power of 2, you're going to have all 1s. And there are nice little patterns we can look for in that. Does somebody else want to tell me what 3 is? So look through our columns, ask yes or no for each one. And if we add these values together, which guesses do we have to get a 3? Yep. See a couple of them coming up there. 1 plus 2 gives us 3, so 0, 0, 1, 1. And now we can add down our columns just like we did before. How much is 1 plus 1? 2. And in binary, 2 is our base, and a base is always written as 1 0. So 2 is too big to write in 1 column, so we have 0 and we carry a 1. Just like we're used to from our regular numbers. Yeah, it's unlike, that's how it is, Dylan. It usually just clicks. You stare at it, look really, really confused, and it's like, oh, wait, there's that pattern. It just kind of pops out at you. So maybe we'll work through a few problems. We're still having trouble seeing the pattern. But same thing here, we're adding. So 1 plus 1 plus 1 is how many? Yep. And, well, we already have 3 in binary written on the board. So that's going to be 1 and we carry a 1. Again, we're back with 1 plus 1 is 2, or 0 carry a 1. And 1 plus 0 is a 1. So if we turn this back into base 10, it looks like we have an 8 plus nothing there. Then we have a 1 in the 2's column. And that's going to give us 8 plus 2 is 10. Which is what we should get when we get 7 plus 3, right? So all of our rules still apply. Subtraction the same way. I'll do the same numbers. 0, 1, 1, 1 minus 0, 0, 1, 1. We're going to work. Actually, I'm going to do 7 minus 2 here, so we can see something. 7 minus 3 was going to leave out an important part from the pattern. Actually, the most important part in the pattern of subtracting. Oh, wait. I'm thinking backwards. Let's do 6 minus 3. That'll work. So 6 is 4 plus 2, and 3 we already saw is 2 plus 1. So here's our binary representation. And if we want to subtract this, that first column is the thing we haven't seen yet, right? What's 0 minus 1? -1, but we want to stay positive, right? So we can do like we did back in elementary school and borrow from our next column. So we'll take that off and we'll borrow a power of 2, which is written 1, 0. So now we have 2 minus 1, and we know what that is. But we took everything away from that column, so we need to borrow again. And again, we have 2 minus 1 gives us a 1. And well, everything else is 0 minus 0.
I got a question.
Yes.
So, when you borrowed the 1, how did it become 2 minus 1? I'm still confused on that.
We borrowed 1 from our next column. But remember, our next column was a power of 2, not a power of 10 like we're used to. So we're borrowing this. We're actually borrowing this 2 when we put that in English.
Okay, so if it was under the 4, it would be a power of 4, so it would be taking a 4.
Mm-hmm. It really,
Okay,
we're
makes
always
sense.
borrowing 2 because we only borrow 1 column over. Right?
Okay, makes sense.
Kind of like when we borrow from the thousands column working in base 10, we only bring that 110 over to the next column.
Okay.
Make sense? And then we have 2 minus 1. So another thing you can see that, well, makes it even easy. Another one of those easy points is we just solve all of our combinations. Okay? We only have a couple of symbols, so we can 1 and 1, 1, 1, 0, 0, 0, 0, 1. There's not as many combinations as we have in all our other digits. So there's a lot less to work with, which is actually the other problem we have. How much time? Oh, I was hoping to finish in about 3 minutes, and this one's probably going to take five minutes. Is it okay if I erase this side? Yeah, so that was just showing all our rules still apply. And usually when we do this, that's when a bunch of messages pop up in the chat room. People say, oh, it makes more sense now. Once we see it a couple times, repetition is very important for learning. So that's all working. But it took a lot of symbols to write these little bitty numbers, right? We're probably going to work with bigger numbers than that. And that's actually what's the hardest part of binary for humans to deal with, is it's too simple for us. We just saw in those 2 equations, we saw every combination of what we can add and subtract. Our minds can handle a lot more than that. Right? We normally work 10 at a time. I pointed out that if you count the sections of your finger, that's what they did in back in Babylon, and counting on our fingers, we can base things up. We can count to 60 really, really quick, which is about the same number of symbols we have in our alphabet, right? The 26 uppercase letters, 26 lowercase letters, some punctuation marks. It's no trouble at all for humans to handle 60 symbols. 2 symbols is way too simple for our minds. And it actually makes it harder for us. So we need to find an intermediate spot, a better base to work with than base 2. But we have some requirements. We need it to go right into a computer. So whatever base we're going to look for to actually work with, and because the binary is too simple, base 10 and base 2 don't line up very well, right? 10's an even number, but 10 also has those 5s in there, right? We get 10 from 5 times 2. So if we take out the even part to try to line it back up with our binary stuff, we still have that 5 that's going to throw everything off. So 10 and 2 don't line up very well. We need something with a lot more the number of symbols that we would have in base 10. So something close to what we're used to working with quantity wise, but that still lines up perfectly with 2s so that it goes directly to binary. And we don't have any extra steps in our translation. So if we start looking for a number that fits those criteria, it has to be built up of 2s. We know 2 is too small. So let's try squaring it. 2 squared gives us 4. That's a little bit better. But we can deal with way more than 4 symbols, right? 4 is still like the human glance. If we glance at the table, we can count more than 4 items on it just at a quick glance, right? What was that question? Sorry, it kind of cut out there for a second. I thought somebody asked a question. Oh, maybe the mic was just left unmuted. So we need bigger than 4, but again, we still have that criteria. We need it to line up perfectly with base 2, so we can only use 2s while we're looking for it. So if we square that again, that'll give us 4 squared, or 16. That's a good number of symbols, right? It's more than the 10 that we're used to, but we can still handle 16 symbols pretty well. It's way less than our alphabet. We count on our fingers, so if we include our toes, fingers and toes, we're well past 16. So that might be a good number to work with. If we check the next one, square that again, 16 squared would be 256. That's probably a little bit big for humans, for us to keep track of. 256 symbols might be a bit too many for us. So 16 would probably be a much, much better base for humans to work with. So base 16, which I didn't leave there arbitrarily. That is the one we actually worked with. It's hexadecimal. We call it hexadecimal. I always forget if it's an I or an A. We call it hexadecimal, but even though we use Greek letters, when we wrote our modern English language, the people who actually listed those out sort of intermingled Greek and Latin. So I always forget whether that's an I or an A. So this might be spelled incorrectly based off that letter right there, but we say it the same, hexadecimal, and that's a lot of symbols. We're Americans, we abbreviate all sorts of stuff, so we just say hex, and other computer people will know what you're talking about. So we're basing things off 16, so we need 16 symbols. Which again, we want to start with our numbers. So 0 through 9 are the first obvious choice, which is 10 symbols. So we still need 6 more. So our first 6 letters are a good option. A through F. Which is still an easy amount of symbols for humans to deal with. You get used to them quick. But starting out here, it's really easy to count those other ones on your fingers. So 0 through 9 are obvious. So A is going to be 10. So you would count 1, 2, 3, 4, 5, up to 10 like normal, or up to 9 like normal. And then when you get to 10, that's just like all your fingers. So that's A, B, C, D, E, F. So those last ones we can count really easy on our fingers as well. Just start with A is another fingers, and B, C, D, E, F. And count those out. It gives us a much nicer symbol to work with.
Can you do that again? I just missed that. Please.
So you count to 9 like normal, right? 1, 2,
Yeah.
3, 4, 5, 6, 7, 8, 9. But then when you get to 10, that 10 is A, because we need it in 1 symbol, not 2, right? 10 usually has 10 symbols. So A, B, C, D, E, F.
So the 5th is
Whichever
A.
you count. Some people like to start on their thumbs, but there's still enough fingers to count that.
Thank you.
But you also, it's not very many, so you'll get used to it very quickly because we actually work in hexadecimal. Anytime we have to actually work in binary, we type it in hexadecimal because that's really typing 4 bits at a time. So things where we want to work directly in binary, such as colors, or to show on the screen, we want to put those directly in binary so that it's immediate control over the red, green, and blue LEDs making up that monitor. So we actually want to do it as a bunch of on, off, on, off, on, off to get our colors. So we would type those in hex digits, and each hex digit is 4 binary bits, which are not too big. I'm going to erase this side from the math. Yeah, it's usually around the middle of the lecture, people are confused, and when we get to that last little part, that's when lots of things tend to pop up in the chat room or in the classroom, see it on people's faces. It starts to make sense once we see it all the way through. So if we have a binary number, I'm going to write another binary number here. I'm going to make one up, 0, 0, 1, 1, 0, 1, 0, 1. And we need to turn this into base 10. Well, we can do it like we did earlier. Go through each column. So we have 8 bits. So from 2 to the 0, 2 to the 7. So we'd have 128. Don't have any 64s. So plus 32, and go through that way. Or a quicker way, instead of going straight from base 2 to base 10, it's actually easier if we go over to base 16 and then back to base 10. And same way, if we have a base 10 number, it actually becomes easier if we go to hexadecimal and then binary. Because to convert this binary number, each hex symbol is going to be 4 bits. So all we have to do is split it up in chunks of 4. And then each 4 bits, we write down the hex symbol that represents that. So 0, 1, 0, 1. What is that 4-bit number in binary? A little smaller than that. That was one too big. Yes. That's that picture I drew on the board earlier. So that's a 5, which is low enough. It's still in our first little symbol, so we don't need any of our letters there. And then we go to the other 4 bits. So we have 8 plus 0 plus 2 plus 1. So what number is that? 1, 0, 1, 1. Huh? And what is 11 in hexadecimal? Because 11 takes too many symbols. We want to write it with just one symbol. We can go back to our fingers to get used to it. So A is 10. So we start at A and B. Well, 11 is the next one after A. So 11 we would just write as a B. So then it's this binary number in hexadecimal is written B5. And now we only have 2 columns to deal with. 16 times, well, I'm going to write times 11 because now that we're doing math, we probably want to look at the numbers we're used to. So a 16s column and a 1s column. We have 5 in the 1s column and 11 in the 16s column. 16 times 10 is 160. And then we have one more 16 after that. So 176 plus 5, and that number is 181 at base 10. So as humans, we can handle chunks of bits at a time. We don't need to go through all 8 of those and add up 128 plus 32 plus 16 plus 4 plus 1 to get back to that number. We can just break it down to binary or break it into 4-bit chunks, find the hexadecimal one, and then write that directly. And vice versa. So if we had 234 in base 10 and wanted to go to binary, it's actually quicker to find this in hex, which the quick way to do it would be divide by 16. So 234, just writing some scratch work over here, which is probably hard to see on the board there. So 234, and we're going to divide by 16. 16 will go into 23 one time. You remember doing long division back in elementary school? We have calculators that can do. We have calculators that do remainder division, so that'll work. But most calculators that would do the remainder division would also do the hex conversion directly for us. So we subtract 16, and we're left with what? 7. And 16 will go into 74. So, 16 times 5 is 80. So that would be too big. So it'd have to be 4, which is 64. So then we have to find this number, divided by 16, and we have 14 with the remainder of 10. We didn't really see that one on the elementary school math review, but did everybody remember that long division? Or we have machines that will do it for us. Just go and do it for the lecture point. So 234 is in base 16. In our 16 column, 16 to the first power column, and our 16 to the 0 power column, which again is a 1s column and a 16s column. So we have 14 in our 6. So when we divide our quotient and remainder, our quotient goes in the 16s column, and our remainder goes in the 1s column. So what hex digit goes in our 16 column here? Somebody want to tell me? Well, I got some more chalk. Which symbol do we use to represent 14? Yeah. An E. And then our 1s column will have a 10. What do we use to represent a 10 in hexadecimal? Yep. EA. 234 in base 10 is EA in hexadecimal, which then to turn that into binary, I have to erase some stuff. Is that okay? So this was just scratch work. We have calculators that will do that for us, but since we walked through a whole bunch of other math, all this stuff's in the way. So 234 in base 10, I should have just wrote up here to begin with, goes to EA in hexadecimal, and then each hex digit is 4 bits. So E, which we found that because it was a 14. What is 14 in binary? Somebody want to tell me what 14 is in binary? Hexadecimal will all fit in 4 bits. Not quite that many. That's 1 too many. All 1s will be 1 less than a power of 2. So all 1s would be 15. So it's actually 1 less than that, right? If we take our 1s column away from there, 8 plus 2, 8 plus 4 plus 2 plus 1. So 8, we're looking for 14. 8 means we have 6 left. So yes, 4 will fit. Means we have 2 left, and then that'll finish them all out. there's the E. Yep. And what about A? What's A? Hexadecimal A, so 10 in normal English. How do we write that in 4 bits of binary? Somebody else want to tell me?
I'm so confused on that part.
So we add up our columns. So we have a. Does that make sense? Who was that that just asked? Was that Dylan?
Yeah, like I understand that the binary numbers, like how
So
to
actually, let's
how to
start
put
at
them.
the biggest one. So A is just a one symbol way we have of writing things, because we're going to do that a lot. Does that make sense?
Yeah.
We're shuffling our symbols around because we didn't have enough. And that's we need it like to represent 16 numbers with one symbol each. We run out of digits, right? So we just use those next few symbols to kind of represent that. So really, when we write A here, that's referring to a 10. So then we'll add up, find the binary number, and that was making sense, right, Dylan? You put a bunch in the chat room, the correct answers in the chat room. So 8 plus 4 would be too big, so we don't have any 4s. 8 plus 2 would give us 10, we don't have any 1s left. So our A and hexadecimal would be 1010. Did that extra little bit help, Dylan? I think that was you were asking. We just needed, we
Yeah.
didn't have enough symbols for what we needed to do.
Makes sense.
Because, yeah, like back to the columns. If we want to write 11, the way we're used to it, we need 2 columns. But if we want to work in base 16, we have to fit that number into one single column. So we just use some symbols we already know to represent those other numbers. And there is our binary representation of that. So we take our base 10 number and find the hexadecimal representation, and then each hex digit becomes 4 bits, and we have our binary representation. Or the other way, if we have binary, we just split it up into 4-bit chunks, and then each 4 bits gets a hexadecimal value, and then we have a lot less columns to add up to find the value of it. So it actually makes things easier, and we have all those symbols on the keyboard, right? So the big one there, Dylan, is if we need to work directly in binary, we don't want to sit there at our keyboard and type 10110101, because as humans, we're probably going to make a typo when we do that for a while, right? We need to cut that down to less symbols so that we're less likely to make a typo. So another way to think of it is we need another symbol to represent those 4 bits. And that's where we use hexadecimal the most. If we need to directly type in binary, we type the hex digits instead of a whole bunch of 1s and 0s. Because humans can keep that straight. That's the main concepts of it. You will see it repeatedly, especially in the situations that you need it as you move forward, right? If you're heading into graphics, web design, or something, you're going to want to deal with colors a lot. And there you'll deal with hexadecimal all the time. You'll have it committed to memory a couple weeks into your website development class. Same thing if you're a network infrastructure person. Is there another word there? Oh yeah, I think it's just network infrastructure. The netty people. That's how you're going to use hexadecimal quite often for typing IP addresses. IP version 6 addresses. The version 4 we still type in decimals, but you'll use that a lot in the situation that is particular to where you're heading in IT. Then you'll see it more, so kind of in preview mode here, But does anybody have any questions about how we represent stuff in binary?
Nope.
Okay, good. Yeah, from all the correct answers and yeses, and I was seeing in the chat room, it looks like that's making sense. And see how it's something that you already knew? You just probably didn't know that you knew it. Previewing it here, you will see it in the situation you need it for. So that's how we make machines store data. We put together our integers, and then once we have our integers, well, we can just do a one-to-one correspondence between our numbers, or between our alphabet, and then we have our whole written language. It's fine for the machine. It's kind of complicated for a human, right? So that's what the machine does, but we need an intermediate level that organizes that nice for a human to work with it, so that we can do our flow of raw data, the raw facts. Yes, the recordings will be available, right? We have the flow of data to information, where we add some context in, make the data useful, and then to knowledge, where we actually apply it somewhere, and then to wisdom, where we gain insight for future use based off the application of that knowledge. From that flow, the binary is not going to work for us. We need something that, well, kind of like hexadecimal, that complicates it up to a level that humans can work with, because we can deal with lots and lots of things at once. And that will be our databases. So we take all that binary code the machine knows and put that in more of a human form, nicely organized as sort of an intermediate mix that's not bad for humans, not bad for a machine. And that way it's optimized for storing and retrieving those raw facts that we need to keep track of. That's databases. We will see that on Thursday. But unless anybody has any questions about binary, I guess that'll be it for today. Wait, 5 seconds. Okay, if you have any questions, let me know. These recordings will be available to us. They should be on, well, since it was asked, let me point out where they're at. Oh, Zoom thumbnails are in my way. As soon as I get the Zoom buttons out of the way, because there's like layers of Zoom buttons in front of my browser tab. So if you go to Ivy Learn, there to our course shell. Actually, there's 2 places. I will send the second one out here in a moment. In our course shell, the Zoom sessions are linked. So if you scroll down to the blue navigation link that says Zoom, there is a tab that says Cloud Recordings, and you will find them here. I also use YouTube for long-term storage, because videos take up a lot of space, and it doesn't take very many videos to burn through the entire like Google Drive or the smallest size of AWS Cloud Bucket or something. But YouTube, we can store lots and lots of videos there. So I use YouTube for long-term video storage. So as this pops up, oh, whoops, I forgot I've been watching honest government ads. Those are hilarious. They're some Australian comedians. I should not recommend them in class because they have foul language, even for the stereotype of angry Australians. Very, very bad language, but very, very funny comedians. So luckily there was wasn't anything too bad in that title. So I use YouTube for long-term storage. So our course is also available here, yeah. Fall 2022. Let me put this in the chat room. Copy and chat. So there is another place where you can get them. And if you go to the YouTube one, it will have what I always call normal video controls, right? Because we get used to YouTube, and then when we go to something like Zoom, it seems like some of our controls are missing, or settings were put in a different place and things like that. especially the speed controls. So that's where all of our videos end up. I usually do that on Saturday mornings. If you want to copy that one from the chat room, or they are available right there in our course shell. Any other questions? Okay, I assume 5 seconds of silence means no questions. So that'll be it for today. If anybody has any questions, let me know. Yeah, this one a little bit long. Our class ends in 10 minutes, but for the next 10 minutes, I'll be sitting here. Otherwise, you can ask me questions anytime, but I will see you all on Thursday and we'll look at databases.